Yeah. Welcome back to all of you. So last time we were discussing the Newton's method and its error analysis. Indeed. Okay. So what we were observing there is that this error at n plus 1th term is satisfying the following type of inequality. That means that mod of en plus 1 is less than equals to c time mod of en square. That indeed we have shown this result already by following the algorithm Newton's method, okay, and using the Taylor series expansion. Okay, so using fixed point technique, what we have done is okay, so we have already discussed this, that okay, so if we use a fixed point technique, so we have defined that our function phi by following relation, and then it can be seen that if you define an interval I indeed in neighborhood of R, okay, a very small neighborhood with length 2 delta, and so delta is in your control, so you can make it however small as possible. So you can show that phi from I to I is continuous, since this is sum of two continuous functions. First function is continuous, this polynomial. Another function is a rational function whose numerator and denominator both are continuous, and they are non-zero in the given neighborhood I, in the interval I, because f dash of R is non-zero, and you use the continuity of f dash, it remain non-zero in neighborhood of R. Okay, so with this we have calculated phi dash of x for the same, and we observe that phi dash of R is 0. Okay, right. So once we have seen phi dash of R is 0, then we certainly inquire about what will happen for phi second derivative at R, what it will be. So means you need to differentiate this phi dash of x again and evaluate at R. Okay, so if we do so, we have phi double dash, and we have used here abuse notation because we have made x as silent character now. Okay, so once you do this and evaluate phi dash at R, then what you observe is that is nothing but the ratio of f double dash at R divided by f dash of R, that is actually evaluated at R, which is non-zero, because f dash of R is non-zero and f second derivative of R is also assumed to be non-zero, because R is a simple zero of f. Okay, so this will certainly tells you that, and so we have, by using the fixed point error analysis, we know that en plus 1 is approximately 1 by q factorial en to the power q f qth derivative, that's will be phi qth derivative at z, you can say z or r, that's r, approximately, because for large enough n, that x approximately at r. So here q value is 2, because phi double dash of R is non-zero, so q value is 2 in there certainly. So once you replace q by 2 here, you will certainly got this relation, and phi second derivative at R is nothing but f double dash of R divided by f dash of R. So this shows that en plus 1 is, so this shows that en plus 1 is big of en square. Okay, that shows this, means mod of en plus 1 is less than equals to c time mod of en square. Okay, so for small n, okay, right, because what you are approximating here f double dash r and f dash of r. So what if I suppose to do here is so indeed you are having en plus 1 if you go for your Taylor series for fixed point result, that's nothing but that is equals to 1 by q factorial en to the power q time phi qth derivative at z, and it certainly depends on r or n, you can say zn. What is zn? Is zn lies between, so zn lies between xn and r, right? But if you use the Taylor series expansion, so if you do it, so qth derivative is continuous, we have assumed, and that is defined on a closed interval, so it's certainly bounded, okay, or it's certainly uniformly continuous, and hence it attains its bound, so you can go for its maximum. So in the case of Newton's method, what you have is en plus 1 is equals to 1 by 2 factorial en to the power q, q is 2 here, and phi second derivative at zn. What is it? Is 1 by 2 factorial en square phi second derivative at zn, that is f second derivative at zn, divide by f dash at zn, okay, which certainly lies on the interval I, which is you can say that is let's say that was okay, that was this was I is equals to r minus delta to r plus delta, and you take, so numerator maximum and denominator minimum over this interval I, okay, so that will be certainly, so you have mod of en plus 1 is less than equals to, if you take the maximum of numerator and minimum of denominator, then this entire quantity will be maximum, so that will be, and that along with 1 by 2 factorial will call at cn square, en square or mod en square, doesn't matter, okay. So maximum of magnitude of this, so certainly we are talking about maximum of magnitude of these values, okay. So what is C is, if I wish to write it clearly, what is C is, so C is, if I recall, 1 by 2 and factorial, okay, and maximum over I mod of f second derivative at x divide by minimum over I of mod of f dash of x, okay. So this establish our result for Newton's method, right? Now, so this is what we have just now discussed, okay. So okay, fine, let's move further. So I have told you just now this inequality C of delta, actually it depends on delta, so it also gives you C of delta. So this delta, brackets with delta, denotes its dependence on delta, okay. So this delta is in your control, so delta you can take however small as possible. So what you will choose is delta in such a way that you have delta times C is less than 1. Why it is so? To establish that actually the Newton's method converges, okay, right. So what it says is, okay, so what if I have this here, so let me Yeah. So what we discussed, so if you necessary you decrease delta, so that we call this quantity as rho, delta times C of delta. Okay, so we call this quantity as rho if I use delta times C of delta, and you can decrease delta so that this rho is strictly less than 1. So what is claimed here in step 6? It is easy to show that this inequality is true. Okay, this inequality is true. So here C is not there. Okay, so this here this is not there. Okay, mod of En is less than equals to rho n time mod E naught. So certainly you are choosing x naught from the neighborhood. Initial approximation must be good approximation. So you are choosing such that mod of E naught, that is equals to mod of x naught minus r, is less than delta. Okay, so what it will gives you is mod of E1 is less than equals to C time mod of E naught square. So look at here. Okay, so which you can write as C time mod of E naught into mod of E naught. But you know, mod of E naught is less than delta. So that will go as delta times C time mod E naught. So delta times C, just now we call as rho, that is mod E naught. That you can certainly make less than mod E naught, which is certainly less than delta. So this actually also tells you this inequality tells you two things. One is mod E1 is less than equals to rho time mod E naught. So one thing what you observe here is mod of E1 is less than equals to rho time mod of E naught, and also it is less than delta. So two things you have here. Okay, so what we will do with this? Okay, so not that mod E naught is also less than delta. Okay, so what you observe here is, so that's what here. So if you look at here, just now we did the same thing. Now for mod E2 is less than equal to C time mod E1 square is equals to, you can write C time mod E1 time mod E1. Okay, C time mod E1 into mod E1. Now mod E1 is less than delta, so you can write that this is mod E1 is less than delta, so this is certainly less than C time delta time mod E1. So that is C delta is rho time mod E1. Okay, so but mod E1 is less than rho time mod E naught. So if you replace it by this, so you have rho square time mod E naught. So mod E2 is less than equals to rho square time mod E naught. Certainly since rho is less than 1, so rho square is also less than 1. So this will be rho square time mod E naught, certainly will be less than mod E naught. Again strictly it will give less than delta. Similarly you can go for mod E3. And you can show that mod E3 is less than equals to, mod E3 is less than equals to rho cube time mod E naught. Since rho is less than 1, so it's all positive powers will remain less than 1. So you can also show that this is less than delta. Keep on doing so. So what it will give you is the actual inequality, that is mod En is less than equals to C rho to the power n time mod E naught. So what will how it will help us now, because since rho is less than 1 and you know that rho to the power n, as n goes large, this tends to 0 as n tends to infinity, and mod E naught is a some number, fixed number, constant number. So the right side tends to 0 as n tends to infinity, and you have this is 0 less than, right, 0 less than equals to. So by sandwich theorem, mod En also tends to 0 as n tends to infinity. So this gives you guarantee that Newton's method converges. Okay, right. Right, so we have done this thing just now. Okay, so next focus on this problem here, That question is, how many iterations are required for Newton's method in order to obtain square root of 2 with 10 to the power minus 6 accuracy? So start with x naught equals to 1. So that's a very near. You know that root 2 is 1.414 something, right? So indeed you can take x naught is 1.2 as well. So it not because so okay. So what it will have is so you can establish the following now. Mod of En is less than equals to C time E naught to the power 2 to the power n. What is C value is? C value is 1 by 2 maximum of mod x minus r less than delta of mod of f double dash of x divided by minimum of this previous discussion we are just following less than delta mod of f first derivative at x. Okay, so now what is r here? R is root 2. Okay, what will be delta? So delta certainly depend on E naught. So we have E naught is, so what is E naught? E naught is equals to x naught minus r mod E naught. So that is equals to mod of 1 minus root 2. Okay, that is something 0.414, that is some right 0.5 approximately, 0.55 or 0.5 approximately. Okay, right, 0.5, which is you are saying equals to delta, let's say equals to delta, which is certainly less than 1. Okay, so we have delta is 0.5. So your int r is root 2. So if I wish to define the interval I, okay, if I wish to define the I interval where we are looking for is root 2 minus 0.5 to root 2 plus 0.5, that is our interval I. Okay, so now you have the mod E naught value, that is 0.5. Okay, so you need to determine the value of C. So what is f of x? What is f of x here is, if I look at carefully, so what I wish to find? Root 2. In order to obtain root 2, so we need to determine an x such that x equals to root 2. So what you will get the equation, okay, what you will get the equation is f of x equals to x square minus 2. So from here, so because we are interested in x equals to root 2, x such that x is root 2, so means x square minus 2 equals to 0. So this will give you the equation for f of x. First, certainly you will get f dash and f double dash, and you know that I interval is lies on the positive x axis. So this certainly increasing, this is fixed constant. So you will certainly able to get the minimum over I, that is at the left hand point of the interval, and this remains constant. So this is 1 by 2. So this value of maximum is 2, and this value is minimum is 2 times square root of 2 minus 0.5. That is a minimum value, right, because since it is increasing over the this interval. And if you approximately, you will get it is 0.55, that is approximately 1 by 2. So C value is 1 by 2. Okay, so then you just fix this in this following relation. Mods of C time En is less than equals to C time E naught to the power 2 to the power n. So once you relate here and you try to solve this by replacing C values, what you will get is number of steps required are n equals to 4. Now what remains here now is to establish this inequality again. Okay, so this inequality can be established by just following the thing, following this here. So looks here. So what just now we have established the following, right? Mod of En plus 1 is less than equals to C time mod En square. Okay, so certainly if you multiply both side by C here, so what you will get here? C square time mod of En square, which you can write as C time En whole square. So from a more relation we get the following. So you just try to, so if you replace n by n minus 1, you will get this. So this here, and certainly you have, so this if you collab with the following this inequality, what you will imply is mod of C time En plus 1 is less than equal to C time En minus 1 to the power 4. So if you look at clearly, it is 2 to the power 1 here. It is 2 to the power 1 here. It is 4 is 2 square. Now if you follow for the next step here and replace n by n minus 2, then you will get the following. And if you use this here, you will get the following. So now you see this 8 is 2 cube and so on. So and if you follow the pattern, what you will get the actual inequality which we want to claim. Okay, so this will give you establish the following inequality, and with the help of this inequality now you will be able to state that how many number of steps are required for achieving a desired accuracy. Fine, right, fine, okay, thank you.